Okay. I haven't been in this room since last fall, so hopefully the technology doesn't crash on me. If it does, I've got backup, so y'all just kind of bear with me. But it's known for kind of just going out, so hopefully it won't while we're in here this semester. Okay, chapter 1. Let me get, how's the lighting? Can you guys see this okay? Let me turn off one of the lights. Yes? No? Maybe? How's that? Good? Okay. All right. Also, if you came in late, you'll want to be sure you come up and be sure I've got you on attendance, because I don't know you guys yet, so I can't just mark you off. Okay, chapter 1, the foundations of chemistry. Okay, so we're going to look at matter and energy. We're going to look at what chemistry means, states of matter, chemical and physical properties, chemical and physical changes. We'll do a couple exercises with that. We're going to look at the terms mixture, substance, compound. These are terms that are used interchangeably, but we don't always use them correctly. So we're going to look at how to use these terms correctly. And then we're going to hopefully get to measurement. So this is where we're going to look at how do we report measured numbers correctly in lab as well as in class. Okay, and then later on, what's today? Wednesday? So Monday, we will finish up chapter 1. So we'll look at converting from one unit to another. So that conversion factor sheet, that is also posted on Blackboard. You want to be sure that you have that on Monday. Okay, so why is chemistry important to us? Okay, well, my answer simply would be is because it's all around us. It is everywhere. So from our bodies and the chemical reactions that have to take place in our bodies for us to survive, to this tabletop, all contain some shape or form chemistry is involved in order for our bodies to function or for the objects and all the matter around us to exist. So science, it's going to describe properties. So we're going to look at properties of matter, and we're also going to look at energy changes and the changes that that chemicals or matter can undergo. Chem 1, we're more looking at properties, numbers, being able to convert units. And in Chem 2, hopefully all of you will take Chem 2, we look more at energy. We start out looking at heat that's involved in chemical reactions and how that can be dangerous, obviously, if you release a huge amount of heat in a reaction. Okay, but chemistry touches every aspect of our lives. I know to some of you right now this may just seem challenging and kind of scary, but for the most part, it is a basic building block. And once you kind of clicks and you get going with it, it's really not too bad, because it's in our environment, it's in our culture, it's pretty much everywhere. So we're going to look at basic ideas, so the basic principles. Some of my students that have had AP chemistry or they've had higher level chemistry classes, they like even more detail. So if you're one of those people, you can come to me and we can talk chemistry, because I love to do it. But for this class, this is a foundation. This is a basic chemistry class. And so in order to try to ensure that you guys are successful, we're not going to go into intricate detail, because that's for later. That's for people that are really, really interested in the all of the theories and the background. Okay, but I'd love to, I can share some of that with you, but for this purpose, we don't have time to cover all that. Okay, we're going to do the general principles behind chemistry. We're also going to look at solving problems. So hopefully, by the end of the semester, usually word problems, I'm sure you even heard this in high school, word problems are, hard to handle, hard or scary, and they're hard to do. Okay, but hopefully through the rest of the semester, you will get better at that. So you'll get better at solving word problems, real life problems. A lot of my tests will even be titled, one of the sections will say real life problems. Okay, so I want you to be able to incorporate when you have to convert from one unit to another to use this in your everyday life, okay, which you probably already do anyway. So if you were asked to convert from minutes to seconds, I'm sure you've all had to do that. That's a conversion, so something that you've had to use. Okay, so matter is anything that has mass and occupies space, and energy is the capacity to do work or to transfer heat. Okay, and like I said, we're not going to do a whole lot with energy. That's kind of in Chem 2, but we are going to look at matter. Okay, there's just some laws that I'm going to just state here, usually pretty straightforward. But whenever we have a law or a scientific law, or you read that in your book later on, you'll see Boyle's law and Charles' law and all of these kind of gas laws. These are just general statements that, as far as we know, there are no exceptions to this law, to this rule. Okay, now if we do find an exception, then it's no longer a law, and it will change. So over years, you know, chemistry books, they've changed. Okay, and a lot of laws have stayed and held true. Some others haven't. Okay, but to this point, your book is up to date with laws, and we, to this point, have no exceptions to these laws. One of these laws is the law of conservation of mass. And this basically means that matter cannot be created nor destroyed. Okay, so there's kind of a constant amount or quantity of matter in the universe. Okay, also, so when we're looking at chemical reactions, this is going to become very important. Okay, if you start out with 6 atoms of carbon as a reactant, then you're going to have 6 atoms of carbon as a product. Okay, so this is kind of the same idea, goes back to this. You'll see this in practice later. Okay, also for energy, same thing. Energy cannot be created nor destroyed in a chemical or physical change. Now it can be transferred. You can convert from heat energy to electrical energy or mechanical energy. You can transfer, but it's not lost. Okay, it's not lost or destroyed. Okay, these are some theories that, yes. Yeah, you want to come with these printed already, but I can go back for a second. Okay, I can leave here for a second. Mm-hmm. Okay. Okay. These are some theories that we're going to see that kind of hold true through the semester. But the reason these are chosen, there's a few more that they talk about that were theories, you know, since 1808 that haven't held true. But for these, I put the ones that have held true. And these are Dalton's atomic theory. John Dalton was actually an English school teacher, so sounds like a pretty amazing man to come up with these theories in 1808. And to our knowledge, these theories are still true. Okay, so sometimes I don't really get into dates and scientists. I mean, there are some that really stand out that, you know, I want you to know more so kind of later. But it is kind of neat to think about, you know, how long ago this was. And, you know, it's good, you know, if you like to read up on people. But as far as for your exams, there's too many important things for me to ask you, you know, in 1808, what happened, okay? So that's not going to be the basis of your test. I get that a lot of questions about that. Do I need to memorize? No, you don't need to memorize dates. Okay, you just need to know general ideas. But he said that an element is composed of extremely small, indivisible particles called atoms. Okay, and so this was unique at that time and has still held true. We're going to look at the atom. We're going to look at what an atom consists of. Okay. All atoms of a given element have identical properties which differ from those of other elements. Okay, so have any of you ever looked at a periodic table? Okay, forgot that I don't have one up in here. I do in my other classroom. So we will be using the periodic table a whole lot, especially for this first unit. So you want to be sure you've got one in the front of your textbook, or you want to be sure you have one. I'll check Blackboard to see. I can probably post a good one on Blackboard if you want to print that out. But we will be using it a whole lot. Okay, so basically all atoms of a given element are identical. Okay, so can anybody tell me an element that's on the periodic table? Oxygen. Somebody else? Hydrogen. Do what? Okay. Thallium. Okay. Good. So you guys have seen this. So carbon's a big one. That's what organic we mainly focus on. Carbon and sulfur, nitrogen. Okay, so we could go on and on. But all of these atoms in that specific element are identical. Okay. Right. Atoms cannot be created nor destroyed or transformed. Okay. And you can also form compounds. So number 4. So anybody off the top of their head could name a compound? Water, H2O, exactly. And so 4 and 5 kind of go together because compounds are formed when atoms of different elements combine. So you have water, H2O, you've got 2 oxygen atoms and, 2 hydrogen atoms and 1 oxygen atom. Okay, but number 5 says that the number of atoms are consistent in a compound. Okay, so what this means is that it's not just a coincidence that water is H2O. Okay, there's a reason why it's combined in that ratio. Okay, there's a reason why water is not H3O. Okay, because it chemically wants to bond and wants to form that many bonds with hydrogen, or oxygen wants to form 2 bonds with hydrogen. So this is going to be something that hopefully by the end of this first unit, you're going to understand why compounds form in the ratio that they do. Okay, and it's because of electrons, but we'll get there. So an atom is the smallest particle of an element that maintains its chemical identity. They're all chemical and physical changes, so it cannot change. These fundamental particles that build up, or the building blocks of atoms, are electrons, protons, and neutrons. So most of you have probably heard of electrons, neutrons, and protons. Okay, could anybody tell me which one of these, or 2 of these, or all 3, which ones are contained in the nucleus? Okay, protons and neutrons, exactly. So we're going to look at, in Chapter 4, we're going to look in detail about this. What about our electrons? Does anybody know where they are in the atom? On the outside, okay. Very good, but we're going to look at even more detail. They're not just on the outside and in kind of a cloud, as you may have seen. I know when I was growing up, that's kind of what my science teacher told me. Okay, but they're actually, does anybody know what electrons are actually contained in? Orbitals, exactly. Very good. Okay, and when we discuss a molecule, whenever we use this term, this means that we have the smallest particle of an element or compound that is stable. Okay, so you're going to start learning what's stable and what's not. Okay, so this is all kind of preliminary, getting down the definitions, and then we'll put these in practice later. Okay, states of matter. We're just going to run through this real quick because I know most of you already know this. But solids are rigid. They have a definite shape, and their molecules are held really close together. Okay, that's kind of the characteristic of a solid. The difference in a solid and a liquid is that liquids do not have a definite shape. Okay, so if we pour water into this container or we pour it into his water bottle, okay, it's going to assume the shape of the container that you poured in. Okay, so this is different. Okay, molecules are a little bit further apart, can kind of slide over each other. Okay, and they are still held close together compared to that of gases, but they are randomly arranged. Okay. And gases, we actually devote a whole chapter to gases because we have to take into account a lot more properties than we do with solids and liquids when dealing with gases. And one of the reasons for this is because they assume the shape of any container. Okay, so it doesn't matter how big or how small. Okay, and so you also have to look at, pressure. You've got to look at the volume. You've got to look at lots of things when we're trying to do experiments or we're trying to define gases. They expand indefinitely. So this is definitely a difference between a solid and a liquid. And the molecules are very far apart. Okay? So an example of this would be if we were to close off all the leaks in this room so that no air could get out, and we were to release a gas into this room, then it's going to fill this container. Okay, it's going to fill our room. Okay, however, if we open a door, then it's going to rush out and it's going to fill the hallway and everything else. Okay, so that is unique about a gas. Okay, and I'm sure you guys all know when you're dealing with a gas and you put it into, so let's say we have to put a gas into a small container, what do we have to worry about? The pressure, exactly, that it will exert. And so we actually do gas law labs at the end of the semester, and we have to be really careful. Okay, you can't have a closed system. You have to be really careful that you have enough room for that gas to expand. Okay, we can all obviously change states. One thing that is pretty unique, I didn't realize until later, I thought, I'd always seen certain compounds, water can go from a solid to a liquid to a gas. Most all chemicals can do this as well. So it just depends on, they're all going to have different melting, different boiling points, things like that. But for, obviously, for solid water, so ice here, okay, if we melt or if we add heat, then we are going to convert from solid to a liquid. Okay, and then if we further heat, then we know that water vapor can turn to a gas, and you can do the opposite. For gases, we can cool them and consider to be condensing them, so condensation. We can cool a gas and form a liquid. Okay, so we can go in the reverse as well. Okay. When we are observing chemicals and matter, we would like to classify these properties as chemical or physical properties or chemical and physical changes. Okay, so we're going to actually look at some pictures and kind of put these into practice and see that everybody understands. Most people get this pretty quickly. But a chemical property or a chemical change, I always just think of a chemical reaction. So when we start looking at chemical reactions, which is what we're going to look at a whole lot this semester, that's a chemical change. Okay, a new substance is going to be formed. Okay, you can't revert back to the old substance. So you actually have a change in the composition of the matter. Okay, so an example would be chemical reaction. So if we have a combustion reaction, methane and oxygen, and we heat it, we form CO2 plus water. Okay, that's a chemical reaction that's taking place. Rusting is also oxidation. So when your chairs outside that been sitting outside in the rain and in the weather and they start to rust, this is actually oxidation. It's a chemical change that is occurring. Okay, physical properties, there's no chemical composition change. So there's no change in the composition. And things like density, colors, basically what you're observing. So you would say, his shirt's red or hers is white. Okay, so these are, density is also, we're going to talk about exactly what density is, but it is also a physical property. Melting and boiling points, okay, these are just facts. So water has a boiling point of 100 degrees C. That's a physical property. Extensive properties, these depend on the quantity. Okay, so when you're measuring or you're looking at an extensive property like volume or mass, it obviously depends on how much that you have. Okay, whereas an intensive property does not depend on the quantity. Okay, so if we look at this podium, it's brown, but if I only look at this portion of it, it's still brown. It doesn't matter how much I have, it just matters what the color is or the melting point. Okay, a melting point, for instance, is just to the point or the degree with which something melts. So you could have, a large quantity or you could have a very small quantity. Usually you use small quantities when determining melting points. So that's another example. Okay, so I want you to look at these. And one of them is you can look at it in two different ways. So there may not be a direct answer here. But I want you to look at these and label them, and we'll go over them in just a second, label them as physical or chemical change. Everybody got what they think all of them are? Okay, so let's look at the first one, so the top left. Okay, so what did you guys get for this picture? Physical or chemical? Okay, I heard physical. Anybody? Anybody disagree? Okay, why do you disagree? Exactly. So this one, contrary to the fact that you do have a change of color, the changing of the leaf is actually decomposition of chlorophyll. So there's actually a chemical change going on inside the leaf, okay? So this kind of brings to a point that you can have a chemical change that changes color. So you can't always go by color, okay? But I usually get kind of a yes.
So what is an example of a physical change that's color that's not a chemical change?
It would just be looking at a color. So, yeah, observing a color. Yeah, there's not going to be a change. So, yeah, yes. Okay. Well, there's other things too. Like if you add, if you have water and you add dye to it, red dye, they're chemically not bonding to each other. You're just adding that color to water. There's not a chemical change between the dye and the water. Mm-hmm. Okay. What about for the second one? Physical. Okay, good. They're just ice melting. It's a physical change. Okay, what about this one? Chemical. Okay, so you're molding, which is oxidation. Okay, so it's a chemical change. Okay, what about here? Chemical. Okay, anytime you have burning or you have fire, it's going to be a chemical change. Okay, so what about here? Chemicals. I mentioned this on the previous slide about oxidation. So you have rusting. Okay, what about this one? Okay. Anybody get chemical? Okay, why did you think chemical? Okay, so you can look at this one two ways. Okay, he's looking at it as you can't get your boiled egg back to the raw egg. Okay, so that would be chemical. So both answers would be correct here. Okay, physical though would be just what most of you saw of just slicing the egg. Very good. Okay, we just have a few more slides that are kind of definition type things, and then we'll do a little bit more activity and looking at numbers. We use the terms mixtures, substances, compounds, and elements. So we want to go through and be sure that when we use these terms that we're using them correctly. Okay, a substance is matter in which all the samples have identical composition and properties and cannot be broken down by physical means. Okay, we'll talk a little bit more about what does physical means here in a second. Okay, there are two types of substances. So we have elements and we have compounds. Okay, elements cannot be decomposed into simpler substances by chemical reactions or by physical means. Okay, so a lot of you already told me that you know what elements are. You've seen the periodic table. Okay, so basically an element, these are found on the periodic table, okay, is the simplest form of and is a substance. Okay, an element, you can call it an element, or it would be a substance. Okay, but this is the simplest form. We cannot physically take boron or take carbon and break it apart. Okay, we also cannot chemically change boron either. Okay, all right, this is the simplest table, simplest elements. That's why they're all put here. So we can't physically or chemically change them. Okay. However, compounds are composed of two or more elements in a definite ratio. So you guys told me, like H2O. Of course, there are millions of compounds, and hopefully your vocabulary of compounds will increase through the semester. Okay. But these can be decomposed into constituent elements by chemical changes. Okay. not by physical. Okay, remember that this kind of takes a little while to get in your mind, but a substance cannot be broken down by physical changes. So elements and compounds cannot physically be broken apart. So I can't take water molecules and physically myself pull apart the hydrogen and pull apart the oxygen. There's no way for me to do that physically, okay? I can't filter the water, just the water's going to go through. There's no way I can pull apart a compound physically, okay? But chemically you can, thank goodness, because chemical reactions are going on all around us in our bodies. So compounds can react in chemical changes. So they can be decomposed. Hydrolysis or electrolysis is a way that you can actually decompose water. Okay, but there are lots of ways that compounds can be broken down, okay, or converted to different products. So you're going to see this all through the semester. You're going to convert from methane to carbon dioxide or whatever it might be. Okay, so they can chemically change, but physically we can't pull them apart. Okay, a mixture, however, is composed of two or more substances, and each substance has its own property. Okay, so it's not chemically combined to the other substance that it's mixed with. Okay, and you can separate by physical means. Okay, so you have homogeneous mixtures, which means that you can basically, there are no distinguishable parts that you can pull out. Okay, so this would be an example, unless it had a bunch of pulp in it or something. This would be an example of a homogeneous mixture. Okay, so with no pulp in it. Okay, and this would be heterogeneous. I think I had cereal before I changed the picture, but you can pull apart. So you can take out the components of this soup bowl. Okay. Okay, so how could we physically do this? So for here, we could just simply pull them out. Okay, but what's another way that we could physically, let's say, separate maybe salt water, salt and water? Okay, evaporation, very good. Anybody else? You could distill it. That would be a little too much trouble probably compared to just doing evaporating. What else? Somebody else? Filtration, exactly. So those are all physical ways that we could separate the two. So that's the difference. So a substance, we cannot physically do that. We can't take carbon element and run it through a filter. Okay. For compounds, same thing. We can't separate them. They're chemically bound. Hydrogen is bonded to oxygen. We can't chemically, or we can't physically pull that apart. Okay, but chemically we can. We can react compounds with other reactants, and we can form different products. Okay, mixtures, we have homogeneous, we have heterogeneous, and we can physically pull these constituent components apart. Okay, so same idea. I've got some pictures here, and I want you to go through, and I want you to label them as mixture, substance, compound, and or element. Okay, remember a substance, we have two categories under substance. We have element and we have compound. So if you call it a substance, it's probably going to fall under element or compound as well. Okay, so I'll give you guys a few minutes to look at these. Okay, what'd you guys get for first one? Element, exactly, okay. If it falls under element, then what also is it? Exactly. Okay, so copper is on the periodic table of elements. So that's where you can find it there. Okay, what about number 2? mixture, and it's a heterogeneous mixture, right? Because we obviously can see all the components of trail mix. Okay, what about this one? Mixture. Salt water. Okay, so it's mixture. More than likely, probably label it as homogeneous or heterogeneous. Homogeneous, yeah. Picture makes me want to go back to the beach. Okay, what about this one? Okay, compounds. Okay, compounds are also what? Substances. Yes, elements and compounds, we can also call them a substance. Okay, what about here? Looks like we've got some oil and water there. Okay, it would be a mixture, exactly, and it would be a heterogeneous mixture, right? Because we have two. This is actually a good example when we're in the lab of something being insoluble. Okay, it means they're not soluble in each other. You form these two layers when you're looking in the lab. You'll have, we'll do an experiment like that, and you shake it up and you look to see if there's two different layers or if it's all one layer. So this would be an example of two different layers, and it would be insoluble. Yes, somewhat, yeah. Oil is hydrophobic, meaning water hating. We'll go over that. But insoluble and soluble doesn't always have to be with water, though. So we can use different, we could dissolve, ethanol and methanol, or it could be different compounds. But yeah, this would be an example of oil not liking water, so it's hydrophobic. Mm-hmm. Okay, looks like we'll have a little bit of time to get into the use of numbers. Okay, so before we get into actually looking at doing an exercise where you actually are recording measured values, okay, we want to talk about what an exact number is. Okay, anytime I use this term, this means that this is a number that has an infinite number of significant figures. Okay, you don't really quite know what significant figures are yet at this point, probably. Okay, but it means that when we say 1 dozen is 12 things, everyone knows that it's always 12 things. Okay, if you look at your conversion factors list, okay, there's 12 inches in 1 foot. That holds true. Those are exact numbers. So anything on, I think I brought some. Let me see if I did. No, I left them upstairs. I've actually printed a few. I thought, oh yeah, I did. Here we go. Okay, so when you print this, I've got some extras. Anybody doesn't have it printed, but looks like this, and on Blackboard. And these are not all of the conversion factors, but I'm sure some of you have used them. There's 2.54 centimeters and 1 inch. Okay, these are exact numbers. Okay, this is exactly what's recorded, what's tabulated in your textbook. Okay. Okay, we can label an experiment or your results as being accurate or precise. Okay, these two words are not the same thing. Okay, accuracy is how close you are to the measured, known, correct value. Okay, precision is how close your individual measurements are. Okay, procedures in lab usually require you to do an experiment two times or 3 times. You don't just take your first initial observation or number, whatever it might be, and just record that. You usually do it again to see if you get consistency, to see if you get precision. Okay, so that's kind of the standard kind of format for correct lab procedure or technique. Okay, so your individual measurements could be precise, but it doesn't mean that they're accurate. Okay, so let's say you run an experiment and you get 13.1 grams. The second time you get 13.1. And the third time you get 13.2 grams or whatever we're measuring. Okay, those numbers would be precise, pretty precise, especially for the lab equipment that we have here at Calhoun. That's pretty good. Okay, so but you come up to me and you say, okay, I got 13.1 grams. Let's say density, so grams per milliliter. That's what I got is the density. And I say, okay, let me check what you're supposed to have. Okay, well, the density was supposed to be 16.5. Okay, were you very accurate? Not really, but you were precise. Okay, so there's a difference in those two. Okay, what we're going to do is we're going to go through rules on how to correctly tabulate or write down the measured numbers that you measure in lab. Okay, or also if I'm giving you a problem, same type idea. Okay, when you write down significant figures, these are the digits that you believe to be correct by the person or whoever is making this measurement. Okay, so measured numbers is kind of obvious what that means, but just in case. Okay, these are numbers that you would measure in the lab if you're taking the mass or you're taking the volume or you're finding density or length. Okay, these are measured values. Okay, does anybody know why it would be important that we're consistent with respect to how we record our measured numbers? Exactly. So if I call a scientist in Germany or China and I say, I got 2 grams, he's going to say 2 point what? To what? You know, because 2 grams is not near precisely enough for us to measure. Okay, and so it is very important for you guys, especially at this level in, like I said, with us being in academic setting in the lab that we have. You know, most of our equipment does not measure extremely precise, but just to give you an idea of how important this is, for example, in industry or pharmaceutical companies, even research labs, I mean, you have to be correct or you have to know your significant figures out to 6, 7 decimal places at least. Even for, you know, over-the-counter medications, they have to be 0.00001% pure. Okay, so it is important to every decimal and every number in certain situations. Okay, for you guys, it's not detrimental. I might count off a point, okay? But for some people, it is, and it can be very, very detrimental that you are all consistent with respect to the numbers that you record. Okay, so rules. We're going to go through these, and then we're going to look at them, see them in practice. Okay, so all non-zero numbers are significant. Okay, so that's one thing you want to remember. So most of these rules that we're going to look at next are going to be when we do have zeros. Okay, so if it's not a zero, then it is significant. So all numbers but 0. Okay. Leading zeros are never significant. Okay. Leading means they precede that non-zero digit. Okay. Those are never significant. Okay. So if we look at 0.000357, we have 3 significant digits. We have a 3, a 5, and a 7 that are not 0. Okay. The one that usually gives students a little bit of a harder time are the trailing zeros. Okay, trailing means the zeros that follow that first, or the last, or however you want to look at it, non-zero digit. Okay, so we've got 2 scenarios here. If you have a decimal place following this non-zero digit, then these zeros, all of these zeros, are going to be significant. So you can kind of think of it as the person put that decimal place there because they know that those next numbers are measured measured as correctly as the person can make them. Okay, and so we would have 4. However, if you record 3,000 without a decimal place, then we have 1 significant digit. Okay, so if you have no decimal place, these zeros are not significant. Okay, does everybody see that? Okay. All right, embedded, or I call them sandwich zeros. I don't know why that's showing up there. These are zeros in between 2 non-zero digits. Okay, if they're in between those 2 digits, then they are significant. Okay, so here you've got a 0 between a 3 and a 6, a 0 between a 6 and a 4, and so all of these would be significant. So 3, 0, 6, 0, and 4 would all be significant. Okay, I have this underlined. You want to star it as well because you will need this for lab. Okay, so you're always going to measure to 1 estimated digit. Okay, so this is another rule that we want to be sure that we follow. Okay, and so we're going to show you more of what we mean by this, by an activity we're going to do. Also in the lab, you'll start to really figure out what this means. So you're going to look at whatever measuring device that you have, and you're going to look at how it's calibrated, and then you're going to estimate one more digit past what it's calibrated as. Okay. You can also use scientific notation. I want to do a quick, I think I've got just a little bit in here to be sure everybody knows what scientific notation is. But you can also use this for large or small numbers. And just to clarify, if you need 3 and you've got this really long number, then you would just use, if you need 3 significant digits, then you would use 3 here. So how many ever numbers you have before you put in your exponent there, that's going to be how many significant figures are represented. All right. So for this, how many significant figures are represented? Okay. Very good. So we've got, all right, so is this 0 going to be significant? Why? It's leading. Exactly. Okay, what about these two? Because they're sandwiched between a 1 and a 2. Okay, and then what about these two? Okay, because there's a decimal place. Okay, no decimal, not significant. If we have a decimal, these two are. Okay, very good. All right, so I want you to look at these real quickly. Identify the significant and non-significant zeros, or however you want to do it, or just add up how many significant digits that there are total. Okay, I've got 3 here I want you to do. Okay, also notice that in chemistry, we usually don't just write a number. There's going to always be a unit after. Okay, so when you correctly, or to give me an answer correctly, more times than not, you're going to have to also have a unit there telling me what you've measured or what you've calculated, whether it was mass or grams or length. I'll give you just a couple seconds and we'll go over these. Got the answers here following. Okay, so this goes through and explains. So we know that all of our non-zero digits are significant. Okay, did everybody get 4 here? Okay, so we have 3 that are leading, that are not significant, and then we have 1 0 that's following a decimal place. So all 4 of these here would be significant. Okay, what about for B? Did everybody get 5? Okay, so you've just got this 1 0 that's in question, and it's in between 2 non-zero digits, and so we would have 5 there. Okay. What about C? Did everybody get 4? Okay, so we've got an example here where we do not have a decimal place, so these trailing zeros are not going to be significant. So these first 4 here are going to be, the 1 0 4 4 are going to be significant. Okay, any questions on this? Okay, just to look at scientific notation for just a minute, just to be sure everybody has got this. If you have a really small number, so I just have an example of the diameter of the chickenpox virus, just to kind of put this in perspective here, and we have a 0.000003 meters, okay? And so if we want to put this number, it'd be a lot nicer, look a lot neater, and anyone to this length of a small of a number here is going to put it into scientific notation. So if we move our decimal place over 7 times, okay, we move it to right past that first non-zero digit, okay, then we're going to, if it's a really small number, we're going to move it over 7 places, and it's going to be 3 times 10 to the negative 7. Okay, I do get mistakes sometimes on this. Most people do scientific notation just fine, but with this negative and positive. Okay, if it's a really large number, you're going to have a positive number here. Okay, if it's a really small number, then you're going to have a negative number there. Okay. And these are just some you can go through. I won't go through all these. These are kind of some just interesting quantities, I thought, looking at the amount of gasoline that we use in the United States each year. Most of these are really small or really large numbers. But as for, I wanted to show this one. I'm not going to report 68 kilograms as 6.8 times 10 to the 1. Okay, to me, that's actually more work and more like wordiness than you need. So I would just report this at 68. When you start getting past, even 500 is okay, not a very large number, but when you start getting to powers of maybe to the third would be when I would start using scientific notation. For me, for chemists, and from just my experience, small numbers, really very small numbers and very large numbers is when it's convenient and the best practice for using scientific notation. I'm not going to count it wrong. I just don't really see a point in putting 6.8 times 10 to the 1 when you can just write 68. Okay, we're going to do this exercise real quick before you guys go. But we have a piece of paper. We're going to measure it. We're going to find the area. And you're going to discuss with your neighbors or your neighbor and see what they got for their answer. And we're going to discuss how our numbers are the same or how they are different. Okay, so I want you to first write down how long you think that this paper is to the best of your ability. And remember to measure to one estimated digit. Okay, so what that means is that you look at this ruler and you're going to go along how it's calibrated. Okay, but you don't just write 13 point, whatever you think that is. You estimate where it lands in between those 2 points there. Okay, so you estimate one digit. Okay, so everybody take a minute and write down what you think. And that estimated digit is not going to be wrong or right. It's how you, to your best of your ability, how you would record the number. Okay, does everybody have that number? What do you think it is? Okay. What about how wide? Look at our ruler. It's changed, right? Okay, it's not, you can't measure yours precisely here. Okay, but I want you to put down the number for how you would measure the width of the paper. Okay, the paper's black, just to be sure you don't read it the other way. You still estimate one digit. Has everybody got their number? Okay. Okay, now I want you to find the area. So take those numbers and find the area. Length times width. And then once you get that number, I want you to compare it to your neighbor and see what they got. Okay, you guys tell me, what did some of you get for the length? 13.35, 13.37. Okay, so that estimated digit varied a little bit, okay, which is expected. Okay, what about for the width? Okay. Okay, remember you can only measure to one estimated digit. So technically you could only measure as, 8.1. You couldn't say 8.12, okay, because you can't measure as precisely. So technically you could only have two significant digits for the width. Okay, so when you found the area, what did you guys get? Whoa, okay, 109, what did you get? 109, okay. 109.634, okay, so if you were reporting to me, you'd say 109.634, whereas he said 109. That's a pretty big difference. Okay, you've got quite a few decimals that you have that he doesn't. Okay, what else? Anybody? Okay, 109.470, so you're recording it to me in 5 significant digits. He used 3. Okay, anybody else around there? Okay. 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 I'm going to use, obviously, everybody's going to estimate a little bit different. Okay. I'm just going to go ahead and move here. Okay, when you are multiplying or dividing, there are rules that go along with how you should report your final answer. Okay, so like I said, some of you gave me 5 significant digits. Some of you gave me 3. Some of you may have said 4. Okay, this is a big difference. This is a difference. And when you report in your labs or on your homework, on your quizzes, and also scientists around the world, they use this system for recording significant digits. Okay, when you multiply and divide, your product has to have the smallest number of significant figures of your multipliers. Okay, so these are your multipliers here. Okay, so if we look here, we've got 4 significant digits and we've got 3. Okay, these are random problems. We're going to go back to the one that you guys are working on here in a second. Okay, but when you punch this in your calculator, you may get this really long number. So how do you know where to round, what number to give me? Some of you might just want to say, you might write 5. Okay, some people would want to write 5.22. Okay, but what you do is you look at all of your multipliers, and whatever is your smallest number of significant figures in one of your multipliers. Okay, so if we look at these two numbers, what would that be? How many significant digits? 3. So then you report your answer in 3. Okay? Here, we only have 2. Okay, we have this with 5, and we have one with 2. Our smallest number of significant digits is 2, so we cannot report past 2. We're limited by the 2 significant digits. Okay, so I'm just going to use the numbers that I got for the exercise with the paper. Okay, so I think a lot of you are pretty consistent with the team. Okay, I got 13.35. I was able to estimate that 5. Some of you got a 7 or 4 or whatever, and that's fine. That's estimated. Okay. I got 8.2. Okay, some of you may have gotten a little bit different there, but we couldn't say 8.21. We can't measure that precisely because our ruler wasn't calibrated for us to do that. Okay, so we have 8.2. Okay, so when I punch this in my calculator, I think I got about 109.47. Okay, so from this, we're going to have to convert it to the correct value with the correct number of significant digits. Okay, so looking at my multipliers here, how many significant digits do I have to report to? 2. Okay, well, we look here, we've got 109, so what are we going to have to round up to? 110. Okay, remember, that 0 here, if I was to put a decimal there, okay, then it would be significant, but I don't have a decimal, so this 0 is not significant. Okay, does everybody see how I did that? Question? Okay? It's really because you're limited by when you record a number, you have to, especially a measured number. It's not really, I wouldn't say it like fibbing or you're, smudging your results, but you can't measure and report past what you know is to be precise. Okay, so if you're limited by the precision of this ruler, that you could only see 8.2, your final answer can't be more precise than what you're limited by when you measured that number. So if I'm using, for instance, a balance, and it reports to 4 significant digits, well then, if I record my answer and I say, well, I'll just put on some zeros, add 6 significant digits. That's not true. That's not correct because that balance couldn't record to that many significant digits. Make sense? Yes. Yes. Yeah, when you round, so if you need 2 significant digits, you're going to look at that second digit and then round up from there. And then, yes, that 0 is not significant because it doesn't have a decimal. Do what now? For, okay, then one way you could fix that is you could say 1.1 or 1.1 times 10 to the 1 would be a way to fix it. Yeah. Yes. Do what now? Okay. That would be if you needed 3 significant digits. Okay, but you need 2, so you got to go here and round up. So go to that second digit. Okay, a lot of times, especially problems I give you, you'll start seeing a lot of times we'll have 3 significant digits, so that would be the case. But here we have 2, so we have to go to the second and round from there. Yeah, good questions. Okay. Okay, real quick, I'll go through this. Same idea, but we're going to look at the perimeter. So we're going to add. Okay, so there's 2 different rules. When you multiply and divide, we have this rule that we just went over, where you use the lowest number of your multipliers, the lowest number of significant digits. Okay. What about the perimeter? Okay, so you're adding up. So take your numbers. So if you got 13.35, okay, then you've got 2 of those, right? 13.35 plus 13.35 plus 8.2 plus 8.2. Okay, so add up what your perimeter would be. And technically, my units for the area should have been centimeters squared. I forgot to put my units on there. Or inches squared, excuse me. Okay, so add up your perimeter and then see how it differs. See if you got the same thing as your neighbor. Think about how many numbers, how many significant digits you think you should round to. Okay. What are some of the numbers you guys are getting? Okay. 43.1. Anybody else? 43. Okay. Do what? 44. Okay. Okay. Why are you using just 2 significant digits? Okay. Very logical thing to do. Exactly. So if you think about the rule we just went over, then more than likely, if I was sitting in your seat, I'd think, okay, well then when I add or subtract, I need to use the lowest number of significant digits. Unfortunately, there is another rule, okay? And this rule is probably the most forgotten. A lot of students will come up and say, I don't see how. And I'm like, remember, it's not the significant figures you're looking at now, okay? When you're adding and subtracting, this is a more subtle rule than the multiplication or division rule. And your answer has to contain the smallest decimal place of your add-ins. Okay, we're not looking at significant digits anymore. You're looking at the decimal place. Okay, so if we look at this number here, okay, we only, in this last number, we go to the hundredth place. Okay, so it's our least, or it contains the smallest decimal place of the add-ins, and so we would record our number to the hundredth place. Okay. All right, when we subtract, same idea. Okay, so if we have, this is obviously going to be our smallest decimal place, so we're out to 3 places, and so our answer is going to be out to 3 places. It doesn't go along with significant digits. Okay, so let me show this for, okay, so when I added up, let's see, 13.35, 13.35, 8.2, 0.2. Okay. Added all these up. Get 43.1 inches. Okay. So if we were thinking minded of our last rule, like it said, you'd written 43. Okay, but when we add and subtract, we have our lowest number or smallest decimal place of the add-ins, we have the 10th place. So we have to record to 1 decimal place. Okay, does everybody see that? You may want to highlight this one because, like I said, it is the most forgotten of the 2 rules. Okay, when we get here on Monday, we'll pick up with converting. So we'll learn to convert from one unit to another. Don't forget about lab. Have a great weekend and start your homework.